Greetings and welcome to the video for problem set number 1 of Chemistry 223, where we're going to tackle chapter 12 and see what kind of things thermodynamics has to offer us this quarter, which is a pretty fun chapter. Anyway, on this problem set, how this works, you should turn in a self-corrected problem set at the beginning of your lab period. And to do that, here's what I'd like you to do. First of all, try these problems on your own first. Like, don't use this video at first. See how you do, all right? Just kind of make some best guesses and see what happens, and that's totally fine. And then you can use this video to self-correct your work, like see how you did. Some of the problems I suspect you'll get correct, some of the problems you may not get correct, and that's totally fine. You can use this video to see how you do. And when you do this, first of all, you will need a periodic table. I do recommend the periodic table that you can find at mhchem.org/per-tab. That's also in your companion, by the way. This is the periodic table we'll be using this entire quarter. You'll use it on quizzes and exams, so the more you get familiar with it, the easier it'll be and the more efficient you'll be later on. As you watch this video, first of all, you don't have to watch this from beginning to end like a regular movie. You can scrub through it, so at the bottom of your screen, there's probably some kind of little thing that you can slide left and right. You can go forward and backwards as you see fit. Like sometimes you'll need to listen to it in detail, and sometimes you can just kind of skim it. So I do encourage you to do that back and forth. Also, you can change the playback speed on YouTube. You can change it to 1.25 or 1.5 times as fast. I'll sound like a chipmunk, haha, but anyway, it's no problem because it'll make it more efficient to you to get through this. So those are all things you can do, which are totally fine. But whatever method you use, make sure that you self-correct all of your problems. So what I want you to do is put marks next to both the questions you got correct and also make marks next to the problems that you got incorrect. So in the lower right hand corner there is an example of a problem set. You can see that that student got question number 3 correct, and they put little check marks next to it, which are great. You can use check marks, you can use stars, smiley faces, whatever you'd like. All of these symbols are fine, but put some kind of mark next to it so that I know that you got the problem right. On the other hand, if you miss a problem, and that's totally fine, just cross out your old answer. At the very least, put the actual answer, maybe make some notes as to how you would do things differently next time. I'm hoping that this is a learning experience, so it's totally fine to try problems and miss them. Just self-correct them so that you know how to do it better. If you turn in a problem set to me and it's perfect, but you don't have any self-correct marks at all, you will not get full credit. On the other hand, you can miss every problem on a problem set, but if you self-correct all of your work, you will get full credit. So this self-correct thing is really important to me. So mark every problem, show how you get to the answers. Don't just give me the answers, show me the actual work needed to get there. You will be good to go. If you have questions on this material, I do encourage you to reach out to me. You can also talk to the Avid/LSC Tutoring Center located above the library on the main MHCC campus. Their website is mhcc.edu/avid. They offer free chemistry tutoring to you as an MHCC student. They're very cool people up there, and I encourage you to check them out. Without further ado, let's start getting into this problem set. You will need, though, one handout in this problem set. This is a handout that we used back in Chemistry 222, and the title of it is Standard Thermodynamic Properties for Selected Substances. Now, in Chemistry 222, we use the enthalpy table, the delta H formation values, but we're going to use the delta G and the entropy S values in this particular problem set as well. So make sure you have access to this. It is at the end of problem set number 1. You can also find it at mhchem.org/thermo. So either way, make sure you have this in front of you. You will need the values to do this problem set. Okay, let's get into the problem set and see what it has to offer. This is the first of the questions regarding entropy, and entropy is a measure of disorder. And the more ordered something is, the smaller the entropy. On the other hand, the more disordered something is, the higher the entropy. So in the first question there, between pure silicon and what is essentially messy silicon, silicon with junk in it, we would say that the sample of silicon with the messiness, the trace impurities, would have a higher entropy. Things that are messy have higher entropy, and things that are pure would have smaller entropies. Now, the next question is regarding temperature and entropy. We have the same substance, oxygen is a gas, at 0 Celsius and negative 50 degrees Celsius. And entropy increases with temperature. So the O2 at the higher temperature, which in this case would be 0 Celsius, would have a higher entropy. It moves around more. As temperature goes down, the things don't move as well, less disorder, so less entropy. C is about iodine in both the solid and the gas phase at the same temperature, and iodine does exist with both phases arguably at the same temperature. Gases always have higher entropy than solids, so gases have a lot more maneuverability. Solids are very rigid and stuck in place, so if it ever comes down to a question which one has the higher entropy, and you have a gas versus a liquid or solid, definitely pick the gas. Now finally, the last one, notice how C2H4 and N2 have the same molar mass, the same grams per mole. But C2H4 has 6 atoms, N2 has just 2 atoms. So you can imagine that the 6 atoms are going to be more variable, like sometimes the C's will be closer and farther, and the H's could be all close together or all far away, stuff like that. So if you have to guess on something like that, you'd generally say that the more atoms you have, then the more entropy. So C2H4 would be higher than N2 because it has more atoms. And you can see those actual numbers right there that correspond to the true entropy values. The thermo table is the table of thermodynamics and stuff that I mentioned at the beginning of this recitation. You can actually go through and look these numbers up if you'd like to. Using that same table of thermodynamics, we're going to use some of those numbers now to calculate the values of the entropy change. And I want to focus just for a second. This is a change in entropy, delta S. So that's final entropy minus initial entropy. So we're going to use more than one value here. Entropy values by themselves are just S, so there's no delta there. So that's one way to see if you're talking about a change of entropy or just the entropy values. So we're going to use the individual entropy values to calculate the change of energy. And delta, which is change, is always products minus reactants. So for the first one, we would look up C2H5OH as a gas and subtract that value from the C2H5OH as a liquid. And if you do that, this number right here, 281.6, that's the entropy of the gaseous C2H5OH. And this number right here, 160.7, that's the value of the liquid C2H5OH. So notice, by the way, that the gas has more entropy than the liquid, but because the gas is the product, it goes first, and the reactant liquid goes second. So products minus reactants, in this case gas minus liquid, you end up with a positive 120.9. This is a change of entropy that is positive, so it's increasing, and that'll be important for stuff we're going to talk about later on. The second one, we're taking a gas and turning it into a liquid. So again, we've got to look up those individual entropy values. This number right here is the value of the product, which is the liquid. CCl4 is a liquid. And this number is the value of the CCl4 as a reactant, which is a gas. Notice the gas is higher than the liquid once again. So products minus reactants, liquid minus gas. In this one, you're going to get negative 95.3. Entropy here is decreasing. Now, what those numbers mean, if your area gets messier, that's a positive delta S. So on the first one, we're going from a liquid to a gas. That's a positive increase. But the second one, we're going from a gas to a liquid. That's more disorder to less disorder. That's why the delta S value is negative. But more importantly, positive delta S means increasing entropy. Negative delta S means a decrease in entropy for the system. In this question, it says calculate the standard molar enthalpy change, which is delta HF with a little zero up there, for each of the following compounds from the elements at 25 degrees Celsius. And again, I have a little note there. It says recall 1 mole of products, reactants, or elements in their standard states. This is something we actually talked about in Chemistry 222, but it will be helpful to us here in Chemistry 223. So a formation, that little F right there, means a couple of things. First of all, it means that you always have 1 mole of products, and it means that for these type of chemical reactions, all reactants will be elements in their standard states. And once we have the reaction listed, then we can use the delta H of products minus delta H of reactants thing that we did in Chemistry 222. The little sigma, the little E thing right there, means add up all of them. So we'll add up all of the enthalpies of the products and subtract, adding up all of the enthalpies of the reactants. You will need the table of thermodynamic values that's located at the end of problem set number 1. It's also listed at mhchem.org/thermo, whatever you want. For the first one, H2S will be our product, and we're only going to have 1 mole of product. And then the reactants will be the elements in their standard states. So the elements for H2S would be H2, because hydrogen is a diatomic. Have no fear of ice clear brew. Hydrogen's one of them, so we listed H2. Now, sulfur, on the other hand, is an octamer. Sulfur is listed as a S8. Now, normally, I hate using fractions, but with these formations, I have to use fractions as well. If we can only have 1 mole of product, that means there's going to be just 1 H2S, and sulfur comes as 8, so we're going to need to have 1/8 of a sulfur. So the equation, the heat of formation equation then, would be this: H2 gas plus 1/8 of S8, because 1/8 times 8 is 1, which is the 1 sulfur we need, and that's going to make H2S. Oh boy. So again, with the formation constants, you will probably end up using some fractions. I don't encourage that normally, but even I have to use it here. What are you going to do? Anyway, you can look up the different delta H values now in that table of thermodynamics. Products, the H2S, minus reactants, the H2, and the 1/8 of S8 value. Another thing, though, that helps is that when it comes to enthalpy, the elements in their standard states have values of 0. So when you look up the value of H2S, for example, as a gas, it's minus 20.6 kilojoules per mole. Those are the products. And we're going to subtract from it the reactants, which are H2 and S8. But both of those have 0 kilojoule per mole values because, again, they are elements in their standard states. So the delta H for this reaction is literally just minus 20.6 kilojoules per mole. That's a nice thing about enthalpy. The elements in their standard states have values of 0. We don't have to worry about them. And in this case, the heat of formation for making H2S is negative 20.6 kilojoules per mole. This is an exothermic reaction. Heat is being given off because it's a negative value for delta H. If delta H would have been a positive number, it would have been endothermic. We would have had to add energy in, but in this case, it's negative exothermic energy is given off. Okay, for the second one then, like before, Li2CO3 will be the only product and just 1 mole of it. And then the reactants here will be lithium metal, because Li2, that's going to be lithium. We're going to have carbon as graphite. That's the most common form of carbon. And we're also going to have O2 gas, because O2 gas is the most common form of oxygen. But you can probably see that lithium carbonate has 3 oxygens. Oxygen comes in O2s. So yep, we're going to have some fractions. So the reaction then will be 2 lithium solids plus graphite plus 3/2 O2. 3/2 times 2 is 3. That's the number of oxygen atoms we need for lithium carbonate. And we're going to make 1 lithium carbonate molecule. That's the heat of formation reaction. Now, the delta H for this will be products minus reactants, the lithium carbonate minus the lithium graphite and oxygen. But once again, you can see that the lithium, graphite, and oxygen, those are all elements in their standard states. They all have delta H values of 0. So delta H of formation is literally minus 1216.04 kilojoules per mole. So a lot of cool things on this particular problem. First of all, writing a delta HF, 1 mole of product, reactants are elements in their standard states. Also, the elements in their standard states for enthalpy will be equal to 0. So that makes those calculations pretty chill. Now, in the next problem, we're going to look at something similar, but with entropy. You cannot have 0 values of entropy for elements in their standard states. Entropy values will only be 0 for the perfect crystals at 0 Kelvin, which is basically never. So you're going to have to look those up. But for enthalpy, the values are 0. Pretty cool. We're going to find the standard molar entropy change of formation. And notice that little nomenclature. It's a change of entropy, a delta S. The little circle means it's standard states. But if it's a entropy of formation, it gets the little F right there. And what we want to do here is find the entropy of formation for H2S and Li2CO3. And the punchline here is that if you have a problem like this, you want to have 1 mole of product. So H2S would be the only product for the first one, and Li2CO3 would be the only product for B. And then the reactants will be all the elements in their standard states. So it might be just as easy to show you as anything. Again, this is really important there, so I want to highlight again. The little F is important because it's different than the other entropies. You want to have just 1 mole of product, and all reactants are elements in their standard states. And you can look all these numbers up in that table of values. So for the first one, this right here is an entropy of formation. You have 1 mole of H2S on the product side, and that's important. And the reactants are elements in their standard states. So H2 is a gas, all right, so you can see that's there. And sulfur is what they call an octamer. It's 8 atoms altogether. H2 is a dimer. It exists at 2 atoms per molecule, but sulfur is actually an 8. So notice that we have to put 1/8 of S8 in order to make this delta SF equation work. We must have just 1 mole of product there. We can't have 2 or 8 or anything like that. So me, as a chemist who hates fractions, I have to use fractions here. What am I going to do? But anyway, after you figure that out, then delta S is the same as before. It's the products minus the reactants. H2S has a value apparently of this, and you subtract from it all the reactants. So 130.7, that's the hydrogen. And if you look up the S8, it's this number, but we're going to take 1/8 of it because we must have, again, just 1 mole of H2S present. So delta S for this reaction is positive 43.0 joules per Kelvin. Similar thing on the second one, only now we're going to have just 1 mole, Li2CO3, and if we do, then we're going to have just the elements in their standard states on the reactant side. There are 2 lithiums in the Li2CO3 formula, so we'll have 2 of those. Carbon exists as graphite, diamond, and a couple other forms. Graphite is the most stable and common form, so we would use graphite, don't use diamond. Darn it. Anyway, 3 oxygens in lithium carbonate. Oxygen comes as a diatomic, so we need to use 3 halves. 3 halves times 2 is 3. That's how many atoms we want. It's a little weird, but we'll do it. So anyway, you go through and you find the values. 90.17 is lithium carbonate. We need 2 lithiums, so 2 times 29.1. Graphite has this number right here, and O2 is 205.2, but of course we multiply it by 3 halves, and if all is said and done, negative 281.6 joules per Kelvin. So while the first one had an increase of entropy was half happy making H2S. The second one had a decrease in entropy. Entropy was not happy making lithium carbonate, but lithium carbonate is actually fairly common. This is a problem where it wants you to classify each of the reactions according to their spontaneity, and are these reactions enthalpy and or entropy driven? All right, so spontaneity is a term used in thermodynamics to describe when a reaction occurs naturally by itself. All right, spontaneity is really helpful because some reactions you put the chemicals together and something happens, and if something happens, that's spontaneous. On the other hand, sometimes you put chemicals together and nothing happens. Those reactions would be considered non-spontaneous. Now, spontaneous doesn't mean anything about time. All right, so it does. Spontaneous to me kind of sounds like spur of the moment. I'm going to the store. No, it's not that kind of spontaneity. In the thermodynamic world, spontaneity just means a reaction which will occur. So to answer this question, we need to look on the far right side at the enthalpy values, which are those delta H's, and also the entropy values. And the main equation to use here is delta G equals delta H minus T delta S. And spontaneous reactions will always have negative delta G values. So if you have, for example, like on the first one, if you have a negative delta H, that contributes to a negative delta G. So that reaction with a negative delta H is considered enthalpy driven. On the other hand, the other part of that Gibbs energy term, delta G equals delta H minus T delta S, the minus T delta S means that if you have a positive delta S, that's going to also help the delta G be negative. Remember, it's negative T times delta S. So positive delta S means the delta G will be negative. So the first reaction here is definitely going to be spontaneous. Here's the Gibbs free energy equation right there, delta G equals delta H minus T delta S. And remember, we're looking for negative delta G's. So if you have a negative delta H, which we do on A, and a positive delta S, this reaction is absolutely going to be spontaneous. It is enthalpy driven because of the negative delta H. It's also entropy driven because of the positive delta S. So that first reaction will be spontaneous all the time. It's both enthalpy driven and entropy driven. And here's just a little thing that says that delta H less than 0, which means negative, delta S greater than 0, positive, spontaneous under all conditions, both entropy and enthalpy driven. Now, the second reaction with magnesium oxide there, you can see that the delta H and delta S are both positive terms. And delta S positive means that that's going to be an entropy-driven reaction. However, delta H here is a positive number, and a positive delta H contributes to a positive delta G, not the negative delta G that we want. So this reaction is considered to be entropy driven because delta S is positive, but it's not enthalpy driven. All right, enthalpy is not contributing to the spontaneity. This is a case where the thermodynamic quantities delta H and delta S fight, if you will, to see which one's going to be spontaneous. And the temperature of the reaction is going to depend on if the reaction is spontaneous or not. We'll talk about that later. So from this slide, negative delta H's are enthalpy driven, positive delta S's are entropy driven, and if you have both of them, both negative delta H and positive delta S, it's spontaneous all the time, like on A. On the other hand, there's a lot of cases where you have, for example, on B, where one of them's positive and the other one is positive, or they're both negative, something like that, then one of them will be helpful towards spontaneity, and on B, that's entropy. That's why we call it entropy driven, but not enthalpy. Here's a question where we'll need that thermodynamic table we were talking about earlier. And let's calculate delta H and delta S for this reaction, where the silicon 4 oxide, the SiO2, reacts with carbon to make silicon and carbon dioxide. And we like to figure out if this reaction is spontaneous at 298, and is it's predicted to be spontaneous at higher temperatures. And we'll talk about that in a little bit. So the first thing we're going to do on this one is we're going to find delta H and delta S. And to find those, it's always for example, for enthalpy, it would be the delta H of the products minus delta H of the reactants. And we can look up those individual reactants and products in that table and then find the overall delta H. And the same kind of thing for the entropy, delta S, where we'll figure out the entropy of the products and subtract the entropy of the reactants to figure out the delta S and see what's happening. And then finally, to figure out the spontaneity, we'll throw the delta H and delta S into the delta G equation. Delta G equals delta H minus T delta S, and we'll just see what kind of number we get out. If delta G is negative, spontaneous, but if delta G is positive, non-spontaneous. So again, you're going to need that table. We're going to look up those delta H, F, and S values. We'll find delta products minus reactants for both enthalpy and entropy, and then we'll plug it into the delta G. So there's a lot of stuff on this page. Let's go through it one by one. The first part right here is finding delta H. It's delta H of products minus delta H of reactants. But you can see in that equation, it has CO2, but not silicon solid. And on the reactants, it has SiO2, but not graphite. In enthalpy, all elements in their standard states are defined as 0. So we don't need to look up SiS. Si is a solid, and C is graphite. We only need the other ones. And if you do that, you can see how the enthalpy, positive 517.2 kilojoules. This reaction is not enthalpy favored, and that'll be important here in a little bit. Now, moving down to the next one, we need to do the same kind of thing, but with entropy. Entropy values, individual entropies, are always positive numbers. There's never any negatives, and you do have to look up the elements in their standard states as well as anything. So if you do that, you can see how the entropy of silicon and carbon dioxide minus the entropy of the SiO2 and carbon graphite, we end up with this number right here, positive 185.4 joules per Kelvin. So this reaction is entropy driven because it's a positive delta S. It is not enthalpy driven though, because the positive delta H means non-spontaneous. We want negative delta H's for spontaneity. So finally then, if you put this into the delta G equals delta H minus T delta S, you can totally do that. One small tricky thing, if you look back at the entropy, it's in joules per Kelvin. And usually the delta H's and delta G's are in kilojoules. So if you see right here, there's a point where we turn the entropy in joules per Kelvin into kilojoules per Kelvin. You have to add and subtract kilojoules. You can't add like joules and kilojoules. It messes up everything. So when you do that, you get a delta G which is positive, and positive means non-spontaneous. So this reaction is not going to occur right now, all right, at room temperature, which is 25 degrees Celsius, 298. It's a positive delta G, all right? So the magnitude of delta G, the positive number, says it's non-spontaneous. However, if you really wanted this reaction to go, remembering that entropy here, this is an entropy-driven reaction, if you could increase that temperature, the negative T delta S term would get bigger and bigger while delta H would stay the same. So if you want this reaction to go, high temperatures will allow you to make this reaction spontaneous, because as temperature gets larger, the negative T delta S gets larger, and finally it would be bigger than that positive 517.2 delta H value above. So this reaction, we would say, is spontaneous at higher temperatures. This question is somewhat like the last questions. We're going to find the enthalpy change and the entropy change, and we're then going to turn those into a delta G value. And we want to see which ones are predicted to be product favored, and are the reactions enthalpy or entropy driven. So again, very similar to last time. Now, our table does not have the barium hydroxide values, so they're included there and stuff, and you'll see them here in a little bit. So again, just like the last problem, we want to go products minus reactants for both delta H and delta S. The delta H terms are above my red line right there. Again, remember, you don't need to include the elements in their pure states. So that would be hydrogen gas and barium. So it comes down to the delta H for the barium hydroxide minus 2 waters. And again, note that there's a 2 stoichiometry of 2, so we multiply the delta H of water by 2. That comes out to be negative 436.54 kilojoules. And then the next section down here is how to calculate the entropy, delta S, products minus reactants. You have to look up everything, even the elements in their standard states. They'll all be non-zero positive numbers, right? And so you can see there, like barium hydroxide, there's another 2 right there for the hydrogen, and a 2 right there for the reactant water. But when all is said and done, positive 133.4. Now, remembering from earlier discussions, if delta H is negative, it's called an enthalpy-driven reaction, and that's what we have. This value is negative. This is enthalpy-driven. And then also, our entropy here is a positive number. Positive entropies also are driving spontaneity, so we would call this reaction entropy-driven as well. So the last thing is just to plug it into delta G. Delta G equals delta H minus T delta S. Again, we're converting that delta S into kilojoules per mole because usually S is in joules. And when all is said and done, negative 476.29. Now, negative delta G's are spontaneous. This reaction is definitely going to go. It's going to happen. It is both enthalpy driven and entropy driven. It has negative delta H and positive delta S. So both enthalpy and entropy want this reaction to go, and we see that happen with that negative delta G. This is the value of a spontaneous reaction in chemistry. For the second reaction, same kind of thing. This is making benzene, C6H6, from the elements, from carbon and hydrogen gas. Just as before, delta H, products minus reactants, but all the reactants here, elements in their standard states. So literally, delta H is equal to the heat of formation for the C6H6, 49.1 kilojoules. That's a positive number. This is not an enthalpy-driven reaction. Now, entropy, which is the next section down, and again, products minus reactants, we do have to look up the values on this one, even the elements, and that's what the table's for. We're multiplying the hydrogen by 3, and we're multiplying the carbon by 6, but otherwise it's pretty easy. Negative 253.1 joules per Kelvin. This is a negative entropy. This reaction is not entropy driven. So this is neither enthalpy driven or entropy driven. That means our delta G here is by default always going to be a positive number, and that's what we get. We get positive 124.5. So this reaction is not spontaneous because delta G is positive. If delta G is negative, like on the last one, spontaneous, but this one is not. We would call this reactant favored, if you will. It's not enthalpy driven because delta H is positive, and it's not entropy driven either because delta S is negative. This reaction would be a harder one to occur, but there are ways to make C6H6, and we'll talk about those kind of ways later. You can also find delta G values in different ways. In the table of thermodynamic quantities, you have a whole bunch of delta GF reactions, delta G's of formation. So in this problem, we want to find delta G, but we're not going to do delta H and delta S first and then plug it into delta G equals delta H minus T delta S. In this one, we're going to literally use those delta GFs raw, and we're going to go delta G of products minus delta G of reactants. When you look these values up, delta G, like delta H, have 0 values for the pure elements. So some of these will be easy to look up, that you don't have to check them out. So anyway, use the table. Remember that the delta GFs, the heat delta G of formations, will be 0 for the pure elements in their standard states. In this problem, then, that's going to be oxygen, because oxygen's naturally a gas. Take a deep breath, Anyway, that's actually also mercury too. Mercury's natural state is a liquid. So if you do this, delta G for A, products minus reactants, ignore the mercury, ignore the oxygen, so it's SO2 minus H2S, and you can HGS, excuse me. You can look those numbers up in the table, negative 249.5. So this is a spontaneous reaction because delta G is negative. It is product favored, which means we expect their products to be made, which is cool. Now the second one, same kind of thing. Again, you can ignore the O2 because that's the natural state. So 2 times the delta G of water plus 2 times the delta G of SO2 minus 2 times the delta G of H2S. And again, you just look these pieces up in that table, nothing you have to memorize. Delta G here, negative 990.58 kilojoules. Again, product favored. Delta G is negative, so it's spontaneous. This is an alternative way to find delta G. We're going to see there's lots of ways to find delta G. This problem's kind of cool. We're thinking here about calcium sulfate decomposing into calcium oxide and sulfur trioxide. And the question is, let's find the temperature required to decompose calcium sulfate into calcium oxide and SO3. So what that tells me when I think about this is that we should figure out delta H and delta S values, and we're probably going to find that at room temperature, calcium sulfate breaking down into CaO and SO3 is going to give us a positive delta G. It's going to be non-spontaneous. However, I also predict that either delta H or delta S, is going to be favored. So we'll have either a negative delta H or a positive delta S. So if we play with the temperature, we'll be able to change it in order to make that delta G become a negative number. And I'll show you how this all works out. So what we want to do, like I said earlier, is we want to find delta H and delta S first, all right? And then we'll figure out here what exactly is happening in this reaction. We'll figure out what the ideal temperature is when delta G is equal to 0. And the reaction, once again, calcium sulfate goes to calcium oxide plus SO3. So delta H, products minus reactants, all right? And again, the products here are the calcium oxide and the sulfur trioxide and the reactant calcium sulfate. And if you figure out delta H, we get a positive 403.9 kilojoules. And a positive enthalpy means this reaction is not enthalpy driven. Enthalpy is not in favor of this reaction happening. So that's probably why the reaction is so weird. Now, the next one, we're finding out the entropy value, which also is products minus reactants, and you just get those values from the table, and we end up with a positive 188.4 joules per Kelvin. So this reaction is entropy driven. Positive delta S means entropy driven, but it is not enthalpy driven. All right, enthalpy doesn't want this to occur. Entropy does want this to occur. If you do this reaction at 298 Kelvin, i.e. delta G equals delta H minus 298 delta S, you'll find out that delta G is a positive number. It's not going to happen. And we want to find the threshold temperature where the spontaneity begins to occur. And it's pretty easy to do. What you can do is go back to delta G equals delta H minus T delta S, but we're going to let delta G equal 0. And if delta G equals 0, all right, then we can let that equal delta H minus T delta S, and there's delta S being turned into kilojoules again. All of that equals 0. So 403.9 kilojoules equals T times 188.4 divided by 1,000. We're going to set them equal to each other. So we're going to add T 188.4 divided by 1,000 to both sides. And if you end up solving for T, and I recommend you do this as a practice, you get the number 2144 Kelvin. And what this means is at 2144 Kelvin, the delta G value is 0. And we talked earlier how if temperature rises, then the delta S term begins to dominate the spontaneity. Delta S wants this reaction to go. All right, it's a entropy-driven reaction. And at temperatures higher than 2144 Kelvin, you're going to have a negative delta G. Remember, 2144 is where delta G is 0. So temperature numbers smaller than 2144 will be positive delta G's, non-spontaneous. But if you want this reaction to go, a temperature higher than 2144 Kelvin will make this happen. So imagine that you and I are creating a business, and our business for some reason depends on calcium sulfate breaking down to calcium oxide and sulfur trioxide. Well, if we heat up our apparatus to more than 2144 Kelvin, which is possible, I mean, it's not the easiest thing to do, but it is possible, then this reaction becomes spontaneous, and we'll have calcium oxide and sulfur trioxide just bubbling out, if you will. So that's the value of this. In an industrial setting, if you want something to happen, you can usually make it occur. In this question, I'd like you to predict the sign of the following thermodynamic quantities using the information provided. This is going to make you think about what delta G, delta H, delta S, those kind of things will actually be depending on what happens. So the first one, a solid dissolves in water. Predict the sign of delta G. Okay, delta G, if something happens, delta G is going to be a negative number, and the solid is dissolving in water. All right. We don't know anything else about it, but we see something happens. And if you see something happens, delta G is going to be negative. If the solid did not dissolve in water, it just sat there, you would have a positive delta G. But because something happens, the solid dissolved, delta G is going to be negative. B, a solid dissolves in water and the container feels warm. Predict the sign of delta H. So delta H is the enthalpy, of course, and that's all about the heat. And if something feels warm, that means the energy was given off as the reaction happened, as the solid dissolved in water. And if energy is given off, that means it's exothermic. Delta H is going to be a negative number. Exothermic always means delta H is negative. Endothermic always means delta H is positive. So if the container would have felt cold, that would have been an endothermic reaction. Delta H would have been positive. But here it feels warm. Exothermic, negative delta H. C, a reaction occurs, bubbles can be observed escaping from the beaker. Predict the sign of delta S. Okay, the key thing here about this problem is bubbles, because if you recall, for entropy, the entropy of gases is always greater than the entropy of liquids, and the entropy of liquids is always greater than the entropy of solids. So if you see bubbles form, that totally means that delta S is going to be a positive number. The entropy of your system is increasing. Bubbles mean that entropy is happy. All right? That's basically what it comes down to. If you see the gas being used up or something like that, that probably means entropy isn't going to be happening. But wow, if you see bubbles, that means entropy is increasing. Delta S will be a positive number. D, ice forms on the base of a flask, sign of delta H. Well, if ice forms, it's pulling energy from the outside in to make the reaction happen. So the container feels cold, it's even making ice. Delta H in this problem is going to be a positive number. It's endothermic. It's pulling the energy in to make whatever happens. So that means that this delta H sign will be positive. And then finally, two chemicals are added together, but nothing happens. What's the sign of delta G? Hey, if nothing happens, that means delta G is going to be positive. All right. Delta G is negative if something happens. Delta G is positive if nothing happens. So in this case, we would say this is a non-spontaneous reaction. That's another way of saying delta G is positive. Likewise, the first one, because the solid dissolved in water, delta G was negative. That means that's a spontaneous reaction. So hopefully these will help you to kind of see what the signs of delta G, H, and S are all about and make predictions as to what it means for reactions. Okay, so that's it for problem set number 1 of Chemistry 223, and I hope this has been a useful experience for you. If you have questions on the material, I encourage you to check out both the study guide and concept guide for this chapter. They are located both online and in your companion, which are kind of cool. There is also a chapter guide online, which is a digital list of the different attributes which might help you learn the material. And of course, you can reach out to me, the LSC/Avid Center, etc., etc. Thank you for spending your time with me. I really do appreciate it. Good luck with your studying and have a wonderful day.